Hey, Kat, if you
Yeah.
were an angle, you'd be a cute one.
Oh, stop it. No, really, go on.
I don't get it. What's an acute angle?
Well, Crystal, I'm glad you asked because today we're going to go over all kinds of angles, angles that that you couldn't even imagine existed. So, without further ado, welcome to our Module 2 lesson.
Today, you'll learn all about geometry.
Guiding you through this quest will be myself, Crystal Lambert.
Cat Knight.
And myself, Laura Wynn. By the end of today's lesson, you will know how to determine the measurement of missing angles and polygons and what polyhedra are.
Hey, Laura, do you know what a vertical angle is?
Yes, I do. Vertical angles are angles opposite each other when two lines cross. They share the same vertex. Vertical angles are equal. In fact, they are congruent angles. They are also called vertically opposite angles.
What is a complementary angle then, Laura?
Good question, Kat. Two angles are complementary when they add up to 90 degrees, and they also make a right angle. The two angles do not have to be together to be complementary. They just have to total 90 degrees.
Laura, can you tell us what supplementary angles are?
Of course, Crystal. Two angles are supplementary when they add up to 180 degrees. And if you notice, together, they make a straight angle. The angles don't have to be together to be supplementary. They just need to add up to 180 degrees.
Okay, so for this next problem, we're going to look at this crazy tangle of lines. It looks like a confused spider trying to make a spider web made. Which honestly, if I was a spider, this is the kind of spider web I would make. But, you know. Anyway, in this little tangle of lines, we see a set of parallel lines that are intercepted by two other lines.
What did you mean when you said a set of parallel lines?
Parallel lines are lines that are never going to meet, like me and my soulmate. Think of a divided highway or interstate, and in the middle is that long, grassy trees, whatever. You know what I'm talking about. And they never meet. They're always going the same direction, but they're never going to meet. Okay, so now let's jump into explaining our problem. Thankfully, Laura has already explained the idea of supplementary angles. So we see that here we've got 61. It's given to us. And right here there's only one missing angle, so we can easily find it. So now we just need to subtract 61 from 180, and we get 119. Well, now what do we do? Well, Laura has also explained to us the idea of vertically opposite angles. And we see 61, and now we're missing one. Well, let's see. We can do 119 on this side and 61 right here. Well, now we kind of seem at an impasse. Now what do we do? Well, we know that triangles equal 180 degrees. And if you look, here is a giant triangle right here in the middle. Easy as pie. That's why it looks like a slice of pie, because it equals 180. So now we just add these two up and subtract that from 180. And we know the triangle is 180. And when we do that, we get 56. So now, again, we can look back at our supplementary angles to get this missing angle right here. Get 124 and go back to our vertically opposite angles. Do 124 and 56. So now what do we do? Well, now we're going to look at a concept called alternate exterior angles. Since these lines are parallel, that means they have the same exact slope. So when this line is cutting through it and it's an even slope, it's going to meet the same here and the same angle here. So if this is 56, this is also going to be 56. So now we can find this one by doing supplementary yet again. We add these two up and then we subtract that from 180 and we get 61.
Hey, Kat, whenever there's more than two angles, is it always going to be equal to 180 degrees?
Yes, it is. This is actually called a straight angle, which might shock you, but a straight angle is more than just a straight line. So you can have 2, you can have 3, you can have 600 angles, and as long as it looks like a straight line, it's going to be 180 because the angle measurement of a straight line is always 180 degrees. Anyway, now we just have 2 more angles left to find, and we can find them using our vertically opposite angles. We get 61 and 56, and easy as pie, we are done.
So for this problem, We have two types of polygons that we normally discuss. And in this problem, we're talking about concave, but there's also a convex polygon.
What's the difference between a concave polygon and a convex polygon?
Well, the first one we're going to talk about is a convex polygon. And here you see this pink shape is a convex polygon. In a convex polygon, all the points point to the outside of the shape. Next, we're going to look at a concave polygon. And that's what our problem is actually a concave polygon. And some of the angles, and it doesn't have to be all of them, but you may have one or two, and those angles point toward the inside of our polygon. So, for these problems, we use the formula n minus 2 equals 180 degrees to determine the sum of all interior angles.
What does the variable n represent?
The variable n represents the number of sides we have in our polygon. So it doesn't matter, you know, you can have 7 sides or you can have 120 sides, but you will always be able to determine the sum of all interior angles based on this formula. In this polygon, which I like to refer to as a stingray because I think it's a stingray, we have a total of 8 sides. So for this formula, we are going to substitute 8 for the variable n into our equation. So we have 8 minus 2 times 180 degrees equals 1080. The next step is we have to add all of these angles together. So we have 3y, 7y. So you're going to add those all together. 3y plus 7y plus 7y plus 7y plus 3y plus 12y plus 3y plus 12y is equal to 1080. When we do that, we have 56y is 54y is equal to 1080 degrees. Well, what we've learned in previous lessons is we need to get the variable y by itself. So we must divide 54y by 54, and what we do to the left, we must do to the right. So our total is y equals 20 degrees.
How do we know the measurement of each angle?
Well, I'm glad you asked, Laura. So to determine the measurement of each angle, we have to substitute the 20 degrees for the variable y. So for our angles that are labeled 3y, we multiply 3 times 20 degrees, and that gives us 60 degrees. Then we will do the same for 7y, which gives us 140 degrees, sorry. And then we're going to do it again for 12y, which gives us a total of 240 degrees.
For my next problem, I'm actually going to look at the same stingray that Crystal was looking at, but we're going to do it a little differently. We're going to do it more visually to kind of understand how to do this problem. So away with foul equations. We are just going to draw some pictures because it's more fun that way. So
Says you.
So we all know that triangles equal 180. Again, remember, easy as pie, 180, triangle, pi. We got this. We like pi. Anyway, so now let's go ahead and break this down into triangles. We've got 1, 2, 3, 4, 5, and then this last one right here would be 6.
So how do we know where to draw these triangles?
Well, Crystal, I'm glad you asked, because we can't just go drawing triangles willy-nilly, otherwise we probably wouldn't get the right answer. So we have to keep in mind that every triangle has to have at least one side of the original polygon as one of its sides, and it cannot share a side of that original polygon with the other side. So all of these triangles, if you notice, do not share these polygon sides with each other. Okay, so now we're just going to do that same thing that we did with, we're just going to multiply 6 by 180 because there are 6 triangles. And when we do that, we get 1080, just like Crystal got for her stingray, because this is the same shape.
How is this the same as the equation?
Well, for this one, Well, we know that for a quadrilateral, which is a four-sided shape, it's always going to take up two triangles. No matter how the quadrilateral looks, it uses two triangles. So that's why we are subtracting 2, in the original equation. So now, when we subtract 2 from 8, because that's how many sides there would be, there's 6 triangles, which is what we're multiplying by 180 in the original equation. So now we just go ahead and do the same math that Crystal did. My numbers are a little bit different, but same concept. We're going to add all our y's up. I did it. My equation looks a little different because I did multiplication, but again, same concept. We get 72 y's, and we're going to divide that by 1,080. We get 15. And then we go ahead and plug our numbers in. 3 times 15 is 45, and we put our 45s where they need to be. 11 times 15, is 165, and we put our 165s where they need to be. And then last but not least, we get 15 times 15, which is 225, and we go ahead and plug that in.
Hey, Kat, will this work for any polygon?
Yes, this will. Any polygon, of course, once you get into like a 120-sided polygon, which is named, I don't know, a 120-sided polygon, because I don't know the mathematical term. Of course, it might not be as practical as just plugging it in the equation, but you know, if you wanted to draw triangles, you could. Like I said, if you're not an equation person, this is definitely easier, and I'm sorry if you ever come across a 120-sided polygon, but you know, good luck to you if you do. That's all I have to say.
All right. Here we have a regular nonagon, and it wants us to find the measures of the interior, exterior, and central angles.
So what is a nonagon?
Well, Crystal, a nonagon is a type of polygon, and a polygon is a flat figure made up of straight lines, and it's enclosed. Polygons are named for the number of sides they have. So a nonagon has 9 sides, which makes it a 9-sided polygon.
What are interior, exterior, and central angles?
Well, good question. Interior angles are where 2 sides of the polygon meet at a vertex. Another way to remember, interior angles are inside the polygon. And exterior angles are supplementary angles adjacent to an interior angle, which exterior angles are outside of a polygon. So remember, interior is inside, exterior is outside. And central angles are made at the center of a polygon by any 2 adjacent vertices of a polygon. Once you have interior and exterior down, the only angle left to find is the central angle. So let's work our problem. So to find the interior angle, we have n minus 2 times 180 divided by n, which n is just the number of sides. And we had decided that a nonagon has 9 sides. So you plug your number in and you work your formula, which we get 140 degrees for the interior angle. There we go. Exterior and central angle actually have the same formula, 360 degrees divided by n, which is 9, which will give us 40 degrees. So our exterior, or outside angle, is 40 degrees. And then our central angle, the same thing. 360 degrees divided by 9 gives you 40 degrees. So our central angle is 40 degrees. And that's how you find your interior, exterior, and central angles.
So next we're going to discuss a tetrahedron.
What is a tetrahedron?
So a tetrahedron has 4 faces or surfaces. It also has 4 vertices or points and 6 edges. And we're going to think of this kind of like origami when we think about polyhedra.
What is a polyhedra?
So a polyhedron is a 3-dimensional solid figure. Polyhedra is used when we're describing more than one polyhedron. This particular polyhedron is called a tetrahedron because it has 4 surfaces or 4 faces. Each of these black lines that we're looking at, so right here we're looking at it as 4 equilateral triangles that are flat like a piece of paper. And in this instance, we're going to fold it on the black lines, which represent our edges. So everywhere the pink triangle meets the purple triangle, that's going to be an edge also, and we're going to fold on that edge. So next, we're going to show how what our tetrahedron is going to look like when we fold this.
Hey, Crystal, why are there only 3 sides?
Well, we're actually looking at 4 sides. So what we initially are going to see is the large triangle, right? So we see the outside shape of our triangle. But then you have to think of it as we're looking through that face like it's a piece of glass. And what we're seeing, our dotted lines represent edges that are on the backside. So if we're seeing our solid figure sitting on the surface in front of us, we cannot see the back edges of that figure. So the dotted lines represent those back edges. So what we're looking through, the initial face, that's face 1. Then to the left, we have face 2. To the right is face 3. And the one on the bottom is face 4, and that's also called our base. So in our diagram to the left, the purple would be the base, or face 4, of our tetrahedron.
Okay, so I'm going to look at a little bit more complicated polyhedron. And this one is an octahedron, or 8 sides. And you can think of octa, we see it all the time. We see stop signs, you know, sometimes for me when I'm turning right, they're just yield signs, but, you know. Or we can think of an octopus that has 8 legs, arms, tentacles, whatever he has. He's got 8 of them. So we should see 8 triangles here. But a difference is we've got more isosceles looking triangles rather than equilateral. Okay, sorry guys, we had a little bit of technical difficulties. Crystal, can you repeat your question?
Okay, so what is an isosceles triangle?
An isosceles triangle has 2 equal sides and 1 side that is not equal to the other 2. So this is an isosceles triangle, and this is an isosceles triangle. This is an equilateral, and this is an equilateral. Now, when we count these, we should be able to get 8 sides. 1, 2, 3, 4, 5, 6, 7. I'm just kidding. There's the 8th side. We can think of it as this big giant triangle because we're looking down on it, and this big giant triangle would be the base. So this is what's sitting on the table or the desk, whatever. We have this shape sitting on.
All right, now we're going to talk about an icosahedron.
An icosahedron, what?
An icosahedron is a type of polyhedron. A polyhedron is named according to the number of faces it has. A face is just a flat surface of the shape. Ikos in Greek means 20. So an icosahedron has 20 faces. So technically, it's just a 3-dimensional shape with 20 triangular faces, as you can see by the image I've created. You can sit there and count all 20. Remember, the base is the bottom one. So we have 19 showing and then 20 on the bottom.
Wow, that's fancy, Laura. So, woo, I'm not that fancy, but here we go. So we're going to talk about, we're going to take a tetrahedron and we're going to put it in a cube.
What's a cube?
Well, when we think of a cube, we can imagine a square, but we're going to take that square and make it 3-dimensional. So the easiest thing for you to recognize as a cube are blocks, you know, a child's building block, our ABC blocks, those are cubes. So we're going to take our tetrahedron, and our tetrahedron has 4 faces, remember? And then we're going to put this inside our box. But our equation, our problem says we want to put it in this box where none of the faces are flush. We don't want any of the faces to touch, or we don't want the edges to lay flat against each other. And this is what we have. So if you notice, our dotted lines, you know, you look at our lines really good. So D to E, line segment D to E, it is not lying flush with any of the lines, our edges of our box. And then D to B is not lying flush with the edges. So what you can see in this diagram is that none of the edges, or those lines, of the tetrahedron meet up with the edges of the cube. So this is our Team Teach lesson for Module 2, and we hope we have made this a little bit easier.
Bye, all you cute angles. Thanks for joining us.
Bye.